This is 3.3, rational functions. And the word rational in mathematics is just a big fancy word for fraction. Anytime you see rational in math, it means a fraction. And normally our fractions are things like a over b. And with the usage of fractions, you get some inherent characteristics. One of those characteristics is that b cannot equal 0. So anytime you have a fraction, you can never have a denominator equal to 0. And we're not necessarily dealing with single digit type things. So for example, if you had 7 divided by 0, you know that you can't do this, right? So those are just numbers. We're not actually dealing with numerical fractions. We're dealing with fractions where the numerator is a function and the denominator is a function. N of x divided by d of x. Numerator function divided by denominator function. And we're talking about things like x plus 3 squared times x minus 2 divided by x plus 1 times x minus 4 squared. Polynomials in the top and polynomials in the bottom. That idea that your denominator cannot equal 0 has implications for this denominator. This means that x cannot equal negative 1 and x cannot equal positive 4 because of that whole 0 in the denominator thing. All the other x's are okay. You can pick any other x that you want, but you cannot have x equal to negative 1 and you cannot have x equal to positive 4. Because of this, what does this mean as far as the domain? It means that your domain, the x's that you can use in this problem, in this particular one, can be anything you want except negative 1 and positive 4. So if you were to write the idea of the domain in interval notation, it would go from negative infinity to negative 1, union with negative 1 to 4, union with 4 to infinity. And this looks confusing because it's an interval notation. Boy, a picture would be a lot better. And so, okay, we'll sketch a graph of this. And so here's your x-axis, your y-axis. And what we have here are called asymptotes. So we have one asymptote at negative 1 and another asymptote at positive 4. These are vertical lines that the function cannot cross. The graph does not cross these vertical lines. It can approach the vertical line, but it can never cross it. That's what putting a denominator in our rational function does. It creates asymptotes. So we're going to start you out with a quick review of some simple factoring, because sometimes we're not given things in pre-factored format. We have to actually factor them out. And so if you take a look at this first one, it just says simplify this. And all of these can be simplified using FOIL. We're not looking to have you do the quadratic formula on any of these things. And so we're just going to take that numerator and we're going to break it into x plus 5 and x plus 6. That's factoring the top. And then when we factor the bottom, we'll get x plus 5 times x plus 1. And then you'll notice that these top things on the top are multiplied and these things on the bottom are multiplied together. So that means we can cancel entire chunks of stuff that are multiplied together. So this x plus 5, this entire thing, is going to cancel with this x plus 5. So that's going to leave you with x plus 6 on the top and x plus 1 on the bottom. And now we could ask the question, what is the domain of this function? What are the possible x values you can have? And the domain is all real numbers except x cannot equal negative 1. So this symbol that I wrote, it's like a capital R but with two spines on it instead of just one spine. That's a mathematical symbol for all real numbers. It means everything. So all real numbers except x cannot equal negative 1. And if we were to write this in interval notation, it would be negative infinity to negative 1, union with 1 to infinity. So again, simplify. So we're going to factor the top. And I think we can take an x out of every term. So that'll leave us with x squared plus 9x plus 20 divided by, and oh, we could take an x out of every term down there too. So we'll take out an x and we'll have x plus 4. And now let's see if maybe we can factor what's on top. So this is going to become x times x plus 4 times x plus 5 divided by x times x plus 4. And again, what you'll notice, because these are all multiplied together, this x is going to cancel with that x. And this chunk of stuff, this x plus 4, is going to cancel with this x plus 4. So these are gone, and what are you left with? X plus 5. What's the domain of this function? All real numbers, right? We've canceled out the denominators, so there are no numbers that would cause trouble with this one. On this one, we can factor out a 4x. That'll leave us with x minus 2. And on the denominator, we can factor out, what, just an x, right? So that's going to be x squared minus 4. And then you take a look at the top and you say, is that factored completely? You say, yeah, that's factored completely. You look at the bottom, is that factored completely? No. This x squared minus 4 is a difference of squares. So this can be factored into x plus 2 and x minus 2. So now we can cancel an x and an x. We can cancel an x minus 2 and an x minus 2. And I think what we're left with is a 4 on the top and an x plus 2 on the bottom. So that would be our function, 4 divided by x plus 2. And then we would ask the same question, what's the domain? The domain is all real numbers except -2. And there's an asymptote at -2, graphically speaking. We'll get to that in a little bit. In this exercise, what they want you to do is they're actually giving you the pre-factored function, and they want you to identify the domain and the vertical asymptote. In these problems, we don't even have to factor. All we got to do is look at the denominator and figure out what makes it equal to 0. So when you take a look at this guy, this very first one, some of you might be able to do this in your head. 3 is the answer. So that means there's going to be a vertical asymptote at x equals 3. You're going to select this here, and you're going to do copy paste right there, and you're going to change this 4 to a 3. So yeah, all real numbers except x equals 3. But what if you can't do this in your head? What if the denominator is a complicated beast that you just can't, there's fractions or decimals or something going on, you just can't see it? Well, the idea that we're looking at is what makes d of x equal to 0? That's what you're trying to solve. What makes d of x equal to 0? And so you're just going to take 21 minus 7x equals 0. And you're going to solve this. You're just going to use algebra. So how about we subtract 21 from both sides? Negative 7x equals minus 21. Divide by negative 7, divide by negative 7. X equals negative 21 divided by negative 7, which is 3. So if you can't do it in your head, then just take whatever that denominator is and set it equal to 0. It's just like what we did with the x-intercepts, where we'd take the function, we'd set it equal to 0, and that would give us our x-intercepts. When you take the denominator and set it equal to 0, that gives you your asymptotes, your vertical asymptotes. So let's go to the next one. Again, you're just looking at this guy, and I can't do that one in my head, so let's write it down. Negative 2x minus 4 equals 0. Add 4 to both sides, so negative 2x equals 4. Divide by negative 2, x equals negative 2. So this is what makes the denominator equal to 0, and therefore it can't be part of our domain. So the vertical asymptote is going to be at x equals negative 2, and the domain is going to be copy-paste, all real numbers except negative 2. Let's say that we have n of x divided by d of x. How does this equation impact the graph? So there's some characteristics of the graph that we want to look at. Number 1, the y-intercept. Number 2, the x-intercepts. Number 3, the vertical asymptotes. Number 4, multiplicity. So if you're given kind of this standard format, how do we figure out these things? So for the y-intercept, To do the y-intercept, you find f of 0. N of 0 divided by d of 0. So in our case, that's going to be a times negative b times negative c divided by negative e times negative f. You're just going to plug in 0 to the top, and you're going to plug in 0 to the bottom, and whatever number you get, that's going to be your y-intercept. This is important because usually when we start graphing, we'd like to know, is the y-intercept a positive value or is it a negative value? So the y-intercept is a very important piece of this puzzle. X-intercepts. So in order to find the x-intercept, what you're going to do is you're going to take n of x and you're going to set it equal to 0. So to find all of the x-intercepts, you're going to take the top portion of this rational function and say what makes it equal to 0. And in our case, the problem that we're dealing with here, you're going to have x-intercepts at x equals a, b, and c. And we might as well, while we're at it, let's just slap this on a graph. So here's x, here's y, and let's just put, I don't know, how about an a here, a b here, and a c there. So the top portion of a rational function gives us our x-intercepts. It tells us exactly the location of the x-intercepts. For the vertical asymptotes, we look at the denominator. We look at d of x. And what do we do with d of x? We set it equal to 0. So you set your denominator equal to 0, and in this case, we're going to get x equals e and f. And this is the location of your vertical asymptotes. So maybe we'll put one here at e, and we'll put one here at f. So here's your intercepts, dot, 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 and then e and f are your vertical asymptotes. The x-intercepts come from the numerator, the vertical asymptotes come from the denominator. Multiplicity. And there's two types of multiplicity. There's multiplicity for the x-intercepts, and there's multiplicity for your vertical asymptotes. And the two types of multiplicity are odd multiplicity and even multiplicity. So if you have odd multiplicity for an x-intercept, that means it's a pass-through. That means that the graph passes through that x-intercept. There's a sign change. It either goes from a positive y value to a negative y value or from a negative to a positive. If it is even, then you have a bounce back, which means that the graph reflects off of that x-intercept. If it's positive, it stays positive, and if it's negative, it stays negative. When it comes to the vertical asymptotes, maybe the best way to describe this is with a graph. If you have a vertical asymptote and it's odd, so we'll say odd, then what you have is something that looks like this. One goes up, the other one goes down. One side approaches positive infinity, the other side approaches negative infinity. However, if you have even multiplicity with the vertical asymptote, they either both go up or they both go down. They approach the same infinity. Either both approach positive infinity or both approach negative infinity. We'll sketch a graph, and at the same time, we're going to answer these questions. Where's the y-intercept? Where are the x-intercepts? Where are the vertical asymptotes? And then as we do the x-intercepts and the vertical asymptotes, we're going to kind of do multiplicity on the fly, like along with them. So not just location, but multiplicity. All right, so y-intercept. So what we need to do is plug in a 0. So we're going to say negative 12 times 0 minus 2 divided by 0 plus 3, 0 minus 4. And again, I really don't care about the numerical value. I don't care if this is 2 or 222 billion. I really care about the sign. Is it positive or is it negative? And so if we do this one, you actually get 24 over negative 12, which is negative 2, right? So I know that I've got a y-intercept that's down here. And that's important because that will probably be the starting point of my graph. Okay, so that's done. That's the y-intercept. Tell me about the x-intercepts. So the x-intercepts come from the numerator, positive 2, because that's what makes it 0. So at positive 2, I have an x-intercept. And tell me about that x-intercept. Tell me about its multiplicity. It's odd multiplicity, because this is x minus 2 to the first power. And so that means it's a pass-through. So I'm going to put a little O right there, meaning that's a pass-through. So vertical asymptotes, we're going to read off the denominator. Okay, so negative 3, 1, 2, 3. Here's negative 3, dot, 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 and positive 4. And both of these are odd multiplicity, which means that the graph is going to approach different infinities. I don't know which is which, but I know that they're different. Okay, so let's graph it. Starting at my y-intercept, I'm going to approach this x-intercept right here, and what's going to happen? I'm going to pass through it, not going to bounce back. So we pass through. We're going to approach this asymptote. In which way are we going to veer? Up to positive infinity or down to negative infinity? Up to positive. Why? How do you know? Yeah, because we don't have another x-intercept. So it can't veer down, otherwise it'd have to go through the x-axis. We don't have that, so that means this guy's got to veer up, right? Knowing that this is an odd multiplicity asymptote, if on the left side it veers up towards positive infinity, on the right side it's got to veer down towards negative infinity. And now what happens as we keep going to the right? Does this graph ever punch through the x-axis? No, because if it did, we'd have an x-intercept there. So this probably kind of plateaus out and does something like this. It might even do something crazy, like bend around and come back down like that. But I know that it does not pass through the x-axis. Okay, so that's that part of the graph. Now let's go back the other way. So here we are at our y-intercept, and now we're moving to the left. Up. Which way do we go? Up or down? Got to go down because there's no x-intercept. Zoom. And if it goes down to negative infinity on the right, how does it behave on the left? Yeah, positive infinity, right? So it's got to go up like that. And then does it curl down and pass through the x-axis here? No, because there's no x-intercept, and so it does something like this. And that's your graph. And this is a rough graph, right? Like, you would not copy this and print it in a math journal, okay? This is not, it's accurate enough for our purposes. If we want the real graph, then you pull up a graphing software and you plug in the function and you would graph it. But for our purposes, this is good enough. So here's a graph. I want you to come up with the equation. All right. So let's build it. We know it's going to be a fraction, right? And we know that on the top will be our x-intercepts, and on the bottom will be our vertical asymptotes. Okay, hey, let's start with the x-intercepts. So looking at the graph, I could ask, what is your x-intercept? Or I could ask, what do you write in the numerator to represent that x-intercept? X minus 2, because right there is your x-intercept. Any other x-intercepts? Nope. Okay. What about multiplicity? It's a pass-through, so we're good. Yeah, it's a 1. So you could put the 1 there if you want, or you don't have to. Vertical asymptotes. So x plus 2 and x minus 3 is how we represent that in the formula. All right, multiplicity check. Tell me about the negative 2 vertical asymptote. This guy here. Even or odd? Odd, right? 2 or a 1? It's a 1. This is to the first power because it goes to opposite infinities. Okay, what about the 3? This is even. So that means we're going to square that x minus 3 term. So right now we have y equals x minus 2 divided by x plus 2, x minus 3 squared. And I'm going to put an a out in front of this. The a is our scaling factor. So right now we're, 80% done. We've got our x-intercept with its multiplicity. We've got our vertical asymptotes with their multiplicity. Numerator, denominator taken care of. The only thing we need to do is nail this y-intercept. Like, where's the y-intercept? How do we figure out this a? So let's take this y-intercept right here. And this point is 0, negative 1. That's an x and a y. and we're going to plug them into here and solve for a. The 2 and the negative 2 are going to cancel, so you get negative a over 9. And so it looks like a is going to equal negative 1 times negative 9, which is 9. So we put a 9 in front, and we're done. That's our function. So same idea. X-intercepts on the top, vertical asymptotes on the bottom, account for multiplicity, away we go. X minus 1 is the location, and it's squared because it's a bounce back. Vertical asymptotes, x plus 1, x minus 2. If you look at the x plus 1, is it a first or a second power, odd or even? It's a first power, so we'll just leave it alone. But the x minus 2 is an even, so it's squared. And don't forget, we've got an a out in front. The y-intercept is like 0.3. So when I pick this coordinate, 0, 3/10, I'm going to say 3/10 equals a times 0 minus 1 squared divided by 0 plus 1, 0 minus 2 squared. And we'll solve this for a, and then we'll be done. So to solve this, I'm going to multiply both sides by 4 over 1. See how easy that is? Zip, zip. And then you get 12 over 10, which is 6 over 5, 6/5. So when you write this, I would put the 6 in the top and the 5 in the bottom.